Okay, so Chapter 7, Thermochemistry, we finally have some new material, something that we didn't have in Intro Chem. The section really deals with energy of reactions, and energy is the capacity to do work, and work is force applied over a distance. There are different types of energy. Kinetic and potential is like the first big distinction. Kinetic is the energy of motion. Potential is the energy of position. So a lot of times they'll give you an example of holding a ball 6 feet up in the air, and that ball has potential energy, because if I let go, obviously it's going to fall. So there's this energy of position, and then kinetic is energy of movement. Thermal energy we kind of relate to temperature, and that is a type of kinetic energy, because temperature is really a measurement of molecular movement, right? The faster they move, the higher the temperature. The slower they move, the lower the temperature. So thermal is a type of kinetic energy. Chemical energy, that's when we look at bond energies and breaking bonds and forming new bonds. And so that's more of a potential energy. It's this energy that is stored in a compound that we can access through a chemical reaction. Now, the units of energy, typically calories, which we're familiar with if we read nutrition labels. Really the unit is a kilocalorie, but we, for some reason in the United States, just use calories. Not really sure why. I think we're capable of understanding a kilocalorie, but whatever. And a calorie is equal to 4.184 joules. And joules is another common unit of energy. And it is the amount, a calorie is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Then that talks about nutrition labels, right? We use calories on our nutrition labels, but really the measurement is a kilocalorie. If you go over to Europe, they actually label it properly. It says kilocalories. But anyway, law of conservation of energy is just that energy cannot be created or destroyed. There is a system and a surroundings, and energy can be transferred. So what comes to mind when we did chemical and physical properties lab last year or last semester in Intro Chem, if the reaction in the test tube was exothermic, we could feel the release of energy by the test tube heating up. That would be a transfer of heat from the system to the surroundings. And likewise, if the test tube got cold, then that is the surroundings giving energy to the system. And we'll look more at that later. All right, heat and work, just something to read. First law of thermodynamics, right? Total energy of the universe is constant. Goes back to energy cannot be created or destroyed, really. All right, so heat. All right, so what we're going to look at quite a bit in this chapter is heat. And we're going to be looking at a heat exchange between system and surroundings. We're also going to be looking at chemical energy or energy of reactions. On the next page, we're going to start with heat capacity. And so heat capacity is a measurement of a system's ability to absorb thermal energy, right? So temperature would go up, or the quantity of heat required to change its temperature by 1 degree Celsius. And there's these two formulas here. The Q is heat, the C is the heat capacity, and delta T means change in temperature. And that is our formula if we're looking at a system like a bond calorimeter, where you can take methane, for example, and do a combustion reaction of that methane in the bond calorimeter. And the calorimeter can detect how much energy is released in that reaction. All right, but that's for the system. That's for the calorimeter. And every calorimeter will have like a unique heat capacity. And you'll see that in a future example that we're going to do. If we look at a substance, then what we look at is a specific heat or a specific heat capacity. I've seen both terms. And that is a substance-specific number. And what we're looking at, if we go back to when we learned what a calorie was, right? It was the amount of energy required to raise 1 gram of water by 1 degree Celsius. So it makes sense that the more mass of a substance you have, the more heat energy you're going to need to heat the temperature, right, to change the temperature. And also the more of a temperature increase you want to have, right, the more heat you're going to have to put into it. So heat would be dependent on how much mass of the substance you have, what the substance is, right? Some substances heat up very quickly. They're good conductors of energy, like metals. Some, like water, they take a long time, right? So that C is a constant for the substance. And then delta T is your final temperature minus your initial. That's your change in temperature. So first example here, how much heat in joules does it take to raise the temperature of 814 grams of water from 18 to 100 degrees Celsius? So we're looking at a substance, right? And I always refer to this, I've heard this as the MCAT formula. So MC delta T, MCAT. Anyway, so we have our mass of water, our delta T, we're going to go up to a final temperature of 100 degrees Celsius. We're starting at an initial of 18 degrees Celsius. So we want to have a difference of 82.0 degrees Celsius, keeping our decimal place. And then the C again is the constant for the substance. And since we're looking at water, we're going to have this heat capacity or specific heat capacity of water. And we saw on the previous page that was 1 calorie per gram degree Celsius, but a calorie is the same as 4.18 joules. So we have this heat capacity, 4.18 joules per gram degree Celsius. So what that means again is that if I have 1 gram of water and I want to raise the temperature by 1 degree Celsius, I need to supply 4.18 joules of energy. I'm going to go up 82 degrees Celsius and I have 814 grams of water. So how much heat energy do I need? So when it's asking you for heat, we are looking for Q. So we have our mass, 814 grams, our specific heat capacity, 4.18 joule per gram degree Celsius, and our change in temperature was 82.0 degrees Celsius. So if I take my 814 times 4.18 times 82, big number, right? 279,007 joules. Units of degrees Celsius canceled out, grams have canceled out, so there's my energy in joules. And then if we're looking at only 3 significant figures, we can either round this to 279,000 joules or 279 kilojoules. That would be the amount of heat we would need to raise the temperature of 814 grams of water, a total difference of 82 degrees Celsius. Now, water is an insulator, so it has a very high heat capacity. If I look at something like lead, we learned, way back in the beginning, that metals are very good conductors of energy. So their heat capacities are so much lower, it takes much less energy to start changing their temperature. So we're going to take a 454 gram block of lead, different substance, different heat capacity. Initial temperature is 22.5 degrees Celsius. We want to know what the temperature of the lead will be after it absorbs 4.22 kilojoules of heat. So this is actually our Q. We have our mass, we have our heat capacity. We're going to first solve for the change in temperature, right? That much energy into this much lead, what kind of a temperature change are we going to achieve? All right, so if we have 4.22 kilojoules as our Q, mass would be 454 grams. The specific heat capacity, 0.128 joule per gram degree Celsius. And then our delta T is what we're going to solve for. Just real quickly here, you want to look at the heat capacity is given to you in joules, and this heat is given in kilojoules. So I'm going to multiply this by 1,000, and really I have 4,220 joules. And then I will divide that by the 454 grams and that heat capacity of 0.128. And that'll get me to my delta T. So 4,220 divided by 454, and then divide that by 0.128. So we get to 3 significant figures, a change in temperature of 72.6 degrees Celsius. All right, and that's not our final answer. That's just the change in temperature. And what we know is the temperature is going to be going up because we're putting heat into that lead. It's absorbing the lead. So what we're going to do is add that to our initial temperature of 22.5 degrees Celsius. And that'll get us to our final temperature. So final temperature would be 95.1 degrees Celsius. All right, so we did almost the same amount of temperature change as we did with the water. Now, granted, we have less mass, right? But look at the energy difference, right? 279 kilojoules versus only 4.2. So just remember that metals are really, really good conductors of energy. It takes very little heat to start increasing their temperature. And we know that. That's why they're good for cooking, right? So they transfer the energy from the heating element to our food. So the calorimeter that I mentioned earlier, right, this is looking at a system. So when we were back on this previous page looking at our formulas, both of the examples we did so far were looking at substances. So we were using that MCAT formula. All right, so remember, when you're looking at a specific substance, you need the mass, the heat capacity, and the change in temperature. If you're looking at a system, think of this system, a lot of times we can use like the old insulated thermoses that I had when I was a kid, like you could take soup, and same thing now, right? They're just metal instead of plastics. Or no, they don't have to be, but anyway, so you think of this insulated container and imagine some kind of reaction taking place inside that container. And what the system is the container, and we can measure the heat capacity of that container and then know, okay, well, if the temperature on the container went up by this much, then we know that, you know, this much energy was released in whatever it is that we were looking at. So in this example here, looking at a bomb calorimeter, that just means we're going to do a combustion reaction inside the thermos or whatever you want to say. So a calorimeter is a system rather than a specific substance. All right, and it says we've got a 23.9 gram sample of iridium heated to 89.7 degrees Celsius, dropped into 20 grams of water in a calorimeter. And the temperature of the water rises from 20.1 to 22.6. And we want to know the specific heat of the iridium. So this one's a little bit different because if we kind of think about what we've got, I'm going to just sort of draw this picture. All right, so this is my metal. This is the iridium. And we have 23.9 grams of it, and it's at 89.7 degrees Celsius. And what we're going to do is there's going to be this container, calorimeter, and inside that we're going to have 20.0 grams of water, and the water starts out at 20.1 degrees Celsius. When we put that piece of iridium into the water, the iridium is going to transfer its heat, right? And it's going to release that heat to the water. The water will absorb that heat. So the metal is going to cool down, and the water is going to heat up. And it tells us that the water actually goes up to 22.6 degrees Celsius. So I know we were just talking about a calorimeter and a closed system, like a bomb calorimeter. But in this case, the calorimeter is just to say that that heat exchange that occurs between the metal and the water, that none of the heat lost by the metal is lost to the surroundings. So the calorimeter is the signal that says, okay, this is a closed system. So whatever heat exchange happens between metal and water, we don't lose any of that energy to anything else, like to the air or some other part of the system. We're just going to take the metal, put it into the water. When it's submerged in the water, the metal will cool down, as we know, the water will heat up, and that is that transfer of energy. And what we want to figure out is, what is that specific heat capacity of the metal, of the iridium? So what we want to kind of think about here is that the heat lost by the metal is equal to the heat gained by the water. And the only thing that's going to be different is the sign. That if the heat is being absorbed by the water, that's going to be a positive value, right? Heat is being absorbed. And the heat that's lost by the metal is going to be a negative value, right? Because it's losing heat, so negative. That makes sense. So if I use my MCAT formula, the mass of the water times the heat capacity for the water times the change in temperature for the water would be equal to the negative of the mass of the metal times the heat capacity for the metal times the change in temperature for the metal. And we want to solve for the heat capacity for the metal. So we need to think about everything else that we have. We have our mass of water. We've got 20.0 grams of it. We have our heat capacity of water. We saw this earlier. That was the 4.18 joule per gram degrees Celsius. That's a constant. And the change in temperature, I don't know why I stopped, 22.6 degrees Celsius. So our delta T here for the water would be the 22.6 minus the 20.1. So we have a difference of 2.5 degrees Celsius. So we've got our mass of water, our heat capacity of water, change in temperature of water. So we're good on this side. Mass of water, 20.0 grams. The specific heat capacity, 4.18 joule per gram degrees Celsius. Change in temperature, 2.5 degrees Celsius. Okay. Now on the other side, what we have is our mass of metal, 23.9. The heat capacity is what we're looking for. When you think about the change in temperature, here's what's important. The final temperature of the water is also the final temperature of the metal, right? This is the final for both substances, because as the metal cools down and the water heats up, at some point they get to equilibrium, right? And so that 22.6 degrees that was measured as the final temperature of the water is also the final temperature of the metal. Now, remember when we take delta T, we do final minus initial. So if I have a 22.6 final temperature for the metal minus 89.7, which was the initial, that tells me here, and let me show this off to the margin. So change in temperature of the metal would be final of 22.6 minus 89.7, which is negative 67.1 degrees Celsius. All right, and that makes sense because it's cooling down, so your temperature is dropping, right? So you're losing that temperature. And that'll also help because it's going to take care of that negative that we have, right? Because you can't have a negative mass. So we'd have negative mass of metal, 23.9. Again, that heat capacity of the metal is what we're solving for. And then our temperature, negative 67.1, right? So the negative times the negative, that's going to cancel out, so we won't have to worry about that. So the specific heat of the metal, I'm going to take 20.0, multiply it by 4.18, multiply it by 2.5, and then divide both sides by 23.9, and divide both sides by 67.1. And keeping only two significant figures because of that 2.5 degrees Celsius temperature change for the water, I get a heat capacity for the metal of 0.13 joule per gram degrees Celsius. All right, so let me just show you over here really quick how I set that up. So the heat capacity for the metal was the 20.0 times the 4.18 times the 2.5. So taking those three things multiplied together, then dividing both sides by the 23.9 and the 67.1. And that's where I got an answer of 0.13 joule per gram degree Celsius. So we're actually going to do something similar to this in lab. We're going to take a piece of metal, heat it up, all right, and then drop it into a calorimeter, which just means that it's a closed system. So the heat exchange between the metal and the water, that's the only thing we have to worry about. We don't have to worry about, you know, residual heat going through the walls of the test tube and being absorbed by the air or something like that. It'll be an insulated container, or fancy word for that, calorimeter. All right, and as the metal cools down, the water heats up. The final temperature is after equilibrium, so that applies to both substances, the water and the metal. So if we know the mass of water, we know the heat capacity of water, and we know that change in temperature for the water, we can figure out the heat absorbed by the water. Mass times heat capacity times change in temperature. So there's the energy absorbed by the water. That energy absorbed by the water is equal to the energy released by the metal, just the opposite sign. So that's why we have a negative over here. Now that heat is also equal to mc delta T, where m is the mass of the metal. The heat capacity is what we're solving for, And the change in temperature of the metal is, again, it started at 89.7, it went down to that equilibrated temperature of 22.6, so it went down 67.1 degrees Celsius. All right, so the heat lost is because the temperature is negative, the change in temperature. So those two negatives cancel out, so the two negatives become the positive. So then all we have to do here is do our MCAT for the water, divide both sides by the mass of metal and the change in temperature for the metal, and that'll get us our heat capacity for the metal. All right, now the next one is going to look a little different. It says we've got 23.6 grams of calcium chloride dissolved in water in a calorimeter. Temperature goes up from 25.0 to 38.7 degrees Celsius. If the heat capacity of the calorimeter is 1,258 joule per degree Celsius, what is the enthalpy of this change? All right, enthalpy, just looking at heat of the reaction. So essentially what happens is the calcium chloride here, when it dissolves, that is an exothermic process. It releases energy to the surroundings. And so if we were doing this in a test tube, we would feel that, right? That temperature is going up, the test tube's getting hotter. So what we want to look at here is that we have a calorimeter heat capacity, so that's a system, not a substance, right? The calorimeter heat capacity, and the way you know is that the unit is only joule per degree Celsius. There's no mass attached to this. It's a closed system, so it's like specific to that calorimeter. So when you see the units of joule per degree Celsius, then you know it's a system heat capacity, and you only, if you're looking at those two formulas again, right, we're only looking at these two. The heat capacity times the change in temperature will get you to Q. Mass is not included in the units, so that's why we don't have the mass of the calorimeter. All right, so the 1258, first what we're going to do is find Q for the calorimeter for the system. So that heat capacity of 1258 joule per degree Celsius. And what we can see here is that change in temperature, 38.7 minus the 25.0 was 13.7 degrees Celsius. So if I take that 13.7 multiplied by 1258, I get a Q of 17,200 joules. All right, so that was the heat absorbed by the system or the calorimeter. All right, just like what we saw with the metal and the water in the previous example, that is a positive value because it's absorbed by the system. And the heat exchange, what that means is the heat of the reaction of the calcium chloride dissolving is negative the heat for that system or the calorimeter, which means the system or the calorimeter absorbed 17,200 joules. That means that this reaction released 17,200 joules. All right, so that is a negative sign, always tells you that it is an exothermic reaction, right? Energy is released to the surroundings. All right, and that would be for the enthalpy of the reaction. Now, the question is, what is the enthalpy of this change in kilojoules per mole? So first thing I'm going to do is divide that by 1,000. So that's negative 17.2 kilojoules. And per mole, what we had was, it was per 23.6 grams of calcium chloride. And so to convert that to moles, to go grams to moles for the calcium chloride, we just need the molar mass. So calcium 40.08, the two chlorines 70.9, so I get 110.98 for the molar mass of the calcium chloride. So basically 23.6 divided by 110.98 tells me how many moles I had. So if I take 17.2, divide by 23.6, and then multiply by 110.98, what I get here is a Q of the reaction of negative 80.9 kilojoules per mole. And enthalpy, right, we're going to start seeing this delta H or delta E sign. All right, but the delta H is really what we're going to become very familiar with. It's the same as looking at Q. It's a heat, right? It's just we're going to be looking at a heat of a reaction or the enthalpy of the reaction. So enthalpy is a measurement of total energy change due to both heat and work. Not too worried about that, but basically again here the idea is there is an exchange of heat, right? Heat cannot be created or destroyed. So the calorimeter we go through, and if it absorbs 1258 joules for every degree Celsius increase, if there's a 13.7 degrees Celsius increase, that means it absorbs 17,200 joules or 17.2 kilojoules. That was absorbed by the system, then that means that that's the energy released by this dissolution process, right? When the calcium chloride dissolves, it releases 17.2 kilojoules for 23.6 grams of calcium chloride. Then just because the units wanted in kilojoules per mole, changing grams to moles, we get our kilojoules per mole for the enthalpy of that process. That is a good place for me to stop for this first video.